Welcome to this module of Professor Messer's free Microsoft 7680 certification training course. This module is an overview of IPv4 and IPv6. I'm James Messer, and in this module, I'm going to step through some very generic overviews of IPv4 and IPv6. This is from the 7680 requirements configuring network connectivity. And before we dive into looking at the details of Windows 7 and how it uses IPv4 and how it uses IPv6, I wanted to take a step back and give you an overview of the IPv4 and IPv6 technologies. So in this video, we're going to look at addressing, we're going to look at protocols, and we're going to look at different technologies that you'll need to know so that when you get into Windows 7 and you see a lot of these new technologies and the references to some of these protocols and pieces associated with IPv4 and IPv6, you'll know exactly what they're talking about. You've probably heard of IPv6. It's certainly an emerging technology, and it's on the top of mind for many networking professionals. IPv4 is the version of IP, however, that we've been running for a long time now, very, very long time. And it's one that provides us, this 32-bit address space provides us with about 4.2 billion total addresses. Now, if you start doing the math, you can probably figure out pretty quick there's a lot more than 4.2 billion devices out on the internet, and you'd be correct. And one of the challenges we have is the number of addresses that we're using out here is quickly being depleted. We have technologies we put in place like network address translation that do allow us to have more total devices connecting to the network than 4.2 billion, but those raw external public addresses are quickly being depleted. And that's one of the big reasons that everybody's moving to IPv6. IPv6 has a 128-bit address space, which means I can have about 340 undecillion addresses out there. That's quite a few addresses to have. For the 6.8 billion people on the planet, they could have this many addresses each. That's quite a few. If we took a square meter, every square meter of the Earth's surface, we can have 54.5 million addresses in every square meter on the planet Earth if we're using IPv6. So that certainly allows us to have many, many more addresses available. And there's also a number of technological advantages that come with IPv6 regarding the efficiency of the protocol and the ability of the protocol to secure some of the data within those packets. Well, you may be thinking, if there's an IPv4 and an IPv6, what happened to IPv5? This probably won't be on your exam, but it's useful to know that it was a protocol called the Internet Stream Protocol, and it just didn't take off. So instead of duplicating that version number and confusing people, we now have the IPv4, and we jumped all the way up to IPv6. If you were to go into your Windows 7 and perform an ipconfig/all at the command prompt, you'd see a lot of different addresses show up. So you would see, of course, the adapters, the MAC addresses that are here. You would see that you may have an IPv6 address configured. You may not on yours. I think I have manually configured one on mine. There's also something called a link local IPv6 address. So you may see multiple IPv6 addresses on your computer, and we'll talk more when we get to the IPv6 section on why that is. Notice we also have IPv4 addresses as well, and a number of IPv4 subnet masks, default gateways, DHCP servers. Those are also listed here. What I'd like to do is give you an idea of where these technologies came from, how we use them, and which ones are associated with IPv4 and IPv6. I mentioned earlier that the IPv4 address is a 32-bit address, and if we really broke out the addresses, we would break them out in binary form. You can see all of the bits, all 32 bits are broken out right here on this screen. Us human beings represent these different sections of 8 bits in their decimal form. So when somebody says, my IP address is 192.168.1.131, behind the scenes, that address is really made up of all of these bits strung together. That's how your computer understands those. You may see those 8 bits referred to also as a byte or an octet. If you're reading some materials associated with networking, it may talk about the 4 octets of IPv4. That's what it's referring to. So you've got 4 bytes worth of an address here to work with, and because there's only 8 bits available, if you had all of those bits in number 1 and you did the calculation on those, your maximum number that that you could get on any one of these 4 octets in a decimal form is 255. So we have between the number 0 and the number 255 that we can fit into each one of these octets of an IPv4 address. When we did an IP config and we looked at all of the different addresses that were there, we saw more than just one IPv4 address. There was a subnet mask, there was a default gateway, and there were some other addresses as well. And the reason we have these multiple addresses that must be configured on your computer is because our networks are segmented. We have these subnetting of the network that we've done, and that's because we have an internet kind of in the middle of our screen here, and we have routers connected to this network, and we have all of these devices that are plugged into switches and routers on either side across the internet. One of the challenges with networking is that there's a lot of protocols and communication that goes on between all of the devices that are local on a network. And it's just practically impossible to extend that functionality worldwide. Everybody can't sit on the same network. It's something that is a physics problem. You really can't send that many packets over the network and expect everybody to recognize that everybody else is there. We found ways to get around that by splitting the networks up into smaller pieces. We subnet the network. We assign a certain area of the network to have certain IP addresses, and those are those subnets that they may deal with there. And you may have another network over here that has a completely different subnet associated with it. So to be able to talk back and forth, since we're not directly connected, we have to be assigned a subnet mask, and we have to be assigned a gateway that's going to tell our computer where should we go, what router should we go to be able to communicate to other devices over the network. So as we look at these IP addresses and subnet masks and default gateways, just keep in mind we've created these subnets as a way to make our networks more manageable. And with these technologies in place, we're able to connect all of these billions of devices in the world together, and we're able to communicate from one side of the world to the other quite efficiently. If you're going to have an IPv4 device on your network that needs to talk to other devices over the internet, then we need a few things configured on the workstation. The first is an IP address. We need to have an IP address assigned to the computer, and it needs to be a unique IP address on our particular network. You can see an example of this might be the 192.168.1.165, and I want to be sure that nobody else on my network has that 192.168.165 either. To specify what network I'm a member of, we need something called a subnet mask, and you'll often see this written as something like 255.255.255.0. This is a number that's used by the local device, the local workstation, to figure out where does it live in the world, what subnet does it happen to exist on, and it uses this in conjunction with the next number that we're going to look at, which is the default gateway, because if we're talking to devices that are local, we don't have to talk to a third-party device like a router to be able to do that. We can simply communicate to each other. But if we recognize that the device we need to talk to is on a different subnet, then we're going to need to go to the default gateway. And the default gateway is a device that allows the packets from our computer to go outside of our subnet. It really is very simple. We don't even have to think about it. We just send the packets off to the default gateway. It handles them from there, and it handles getting the packets back to us once that device sends a response in the other direction. This IP address of the default gateway has to be on your local subnet. So that's a very important IP address for us, because if we need to talk over the internet, then we're going to need to know exactly what that IP address is of our local default gateway. There's a few IP addresses you may see all the time. They may be IP addresses that start with a 10 dot and a bunch of numbers. It may be the 192.168 range we just mentioned. And the reason you see these so often is because these are addresses that we call private addresses. To talk over the internet, everybody has to have a unique IP address. But as we've seen, there's not a lot of those things available. So we only have 4.2 billion addresses maximum that we could create for everybody in the world. So what we've done is we've created some private address ranges that on our local network, inside of our office space, inside of our organization, we can give people these IP addresses, and they don't count towards those 4.2 billion. These addresses here are some that are used just to communicate locally, and as long as we're not talking out to the internet with these IP addresses will work great for us. One of the things that we're able to do with our routers that do talk to the internet is convert these private addresses out to public addresses with an address translation. We'll talk about that in a bit. But what that allows us to do is really have one IP address to the world, but inside of our organization, we might have thousands of devices, and all thousands of those devices can talk out to the internet and back because of these translation services. If you see an address range that has a 10.000 through 10.255.255.255, then you can certainly have over 16 million addresses there. We call that a Class A address because of the subnet mask associated with those. You'll also see the 172.16 through 172.31, and also the 192.168 through 192.168.255.255. It depends on the size of your network and the type of connectivity that you have as to which address ranges you will use. If you're at home, you probably have a 192.168 address available. If you're out on a large network and you have thousands of devices around your organization, then you probably have a 10 dot network. You use these 10 dot addresses to be able to separate out, have multiple locations, and be able to support millions of devices on your network. There's a few other protocols you'll need to be aware of when working with IPv4. One of these is DNS. This stands for Domain Name System. And if you've opened a browser and you've typed www.google.com, you'll notice that you're able to access Google without actually knowing the IP address of the Google server. And yet the routers and the other networking pieces of equipment on your network somehow manage to get it to that IP address and back. And that's because before anything can go to Google, we have to first convert the name to an IP address. So if you go to www.professormesser.com, behind the scenes, a query is made to a domain name system server, and that server says, oh, you need to go to Professor Messer. I happen to know that IP address is 74.208.221.234. That saves us a lot of time. If we had to remember every single IP address of every place we wanted to go, we would be spending a lot of time typing and no time actually browsing the network. So having that domain name system in place really makes our process much easier for accessing different hosts on the network. An extremely common and an extremely important protocol that we use is one called DHCP. It stands for Dynamic Host Configuration Protocol. DHCP is extremely useful because when we have these large networks that have thousands of devices on them, we want all of those devices to automatically get an IP address. Imagine if you had to go to all 1,000 of those devices and manually assign an IP address and manually assign a subnet mask and manually assign a default gateway and all of those other addresses that we saw earlier. And if you make a mistake and you duplicate them, those two devices are not going to be able to communicate very well either. So with DHCP, we simply turn on our computer. It will find a DHCP server on the network automatically, and it will pull down an IP address, assign it, and the DHCP server makes sure that there's no duplications on our network, no conflicts there. Very, very simple. It is now expected. Everywhere you go, you simply plug in, and if you're communicating on the network, that's because you got an address via DHCP. If you connected to a network and there was not a DHCP server, and yet you were still able to communicate with other devices on your local subnet, then you probably got a special kind of IP address called an APIPA, which is an automatic private IP address. This is something very specific to Windows and some other operating systems. It's one where I don't have to configure anything on my computer, and even if there isn't a DHCP server, I'm able to communicate. I actually get an address 169.254 something. You can see the subnet mask is 255.255.0.0, which means I can have a lot of devices on my network that have nothing assigned to them and no DHCP server, and yet I'm able to communicate just fine. I can talk to my printer. I can pull things from a file server because I'm using these automatic private IP addresses. We mentioned one of the challenges with IPv4 is that there's only a certain number of addresses. And to stave off that depletion of those IPv4 addresses, we have those private IP addresses that we can assign internally to our organization. So we might have a 192.168 address. We might have a 10 dot address. We've got a lot of different options, but those are private addresses. And as a private address, those devices can't directly communicate over the internet. So to allow us to have thousands of devices with our own private addresses able to communicate, we create something called a network address translation device. And usually this is in a router or a firewall. And this device is the one that is directly connected to the internet. And its job is to take any of these private addresses. And if anybody's talking to the internet, it simply converts the source to look like it's coming directly from that router. And as the traffic comes back, its job is to reconvert it back and send it off to its original source. This is really functional, allows us to have thousands and thousands of devices with our own private addressing scheme, and yet all of those devices can easily communicate out to the internet. It's one that provides efficiency and flexibility in our ability to have any type of addressing we wanted, but also allows us the functionality to communicate out to the internet. All of those addresses and technologies that we've looked at so far have been really based in IPv4. IPv6 is a very different animal, though. And if we look at this, you can actually see why. This is an IPv6 address. One thing you'll notice is you don't have that very simplified 4 octets to pull through. In fact, you've got quite a few number of bytes. You've got 16 bytes of an address to look at. That's 128 bits, so a much larger address to deal with. If we took a single IPv6 address and we split it apart, you can start to see how big that really is. And notice that we don't represent these addresses as decimal anymore. We represent them as hexadecimal, so a little bit more complex in the way that we are looking at those addresses and referring to them. We've also got places where we can abbreviate this to make it a little bit easier. If you have these runs where you have a lot of zeros strung together, you can collapse that into 2 colons here, and it just naturally assumes that everything between those colons is all zeros, so that sometimes will make it a little bit easier to write or at least keep track of those. But even so, that's still a pretty complex address, even with the abbreviations that you can do there. If there's a 0 at the beginning, you can get rid of the leading zeros as well. That helps a little bit. You'll notice that that's a difficult address to remember, even harder than the 192.168.1.1. This was one that you're going to have to really rely on your name services. So just as we had our DNS in version 4, IPv4, we also have a DNS that is in IPv6, and its job is to do a similar thing. We can type in IPv6 for Google's address, and it will return to us the IPv6, real IPv6 address if we need to communicate to the Google web server. When we start talking about these packets that are flying all over our networks, we have a couple of different ways we can refer to them. If we talk about a unicast packet, what we're really referring to is a packet that started on our machine and it was destined specifically for another workstation. It really isn't going to anybody in between. It's a communication from one device to another. A multicast is a different kind of communication. That's where I can send out one packet and multiple devices may be configured to receive that single packet. You see this a lot if somebody's broadcasting video. They'll broadcast it in a multicast form so that you can subscribe to that, and that single device may send out one packet, but at the end stations, there may be hundreds of devices all receiving that one packet at the same time. It's a very efficient way to communicate in that manner. In IPv4, we have this concept of a broadcast where I can send out one packet and every device on my network is already pre-programmed to receive that specific kind, that special kind of broadcast packet. That gets kind of noisy though. So when we came out with IPv6, we came up with this idea of an anycast packet. There are no broadcast packets in IPv6. An anycast packet is designed so that when I send out that anycast, only the local, the most closest, the nearest device is going to receive that packet. And that makes the efficiency of the network much better. We're not sending one packet and blasting it out to everybody. We're being much more specific with where that packet's going. In IPv6, there's also a number of unicast addresses that your computer might be using. One is a global address, and that's the address you would use if you really did need to communicate out to the internet. You use that global address, and that's the one that's used when you transmit that traffic. If you just need to communicate locally, maybe on a campus, between buildings, for instance, that communication isn't going to go to the internet. You might use a different kind of address for that called a local address. It does not go to the internet, and you'll often see it beginning with FC00. It's a good way to tell that that is your local address. There's also a type of address that will only be communicated on your local subnet. So this is very, very local. We call that a link local address. And those addresses start with FE80 at the beginning. So if you ever see those presets, those precursors to those addresses, you'll know right there that that is a local address or a link local address. Well, as you've already been able to tell, IPv4 and IPv6 are very, very different technologies. Really, the name is very similar, but other than that, there's not a lot of things that are identical between those two. And if you're configuring a single workstation, you may configure it both to have an IPv4 address and an IPv6 address at the same time. We call these a dual stack device, and you can start to see exactly an IPv4 address might be configured. And one easy way to convert from IPv4 to IPv6 and assign an address that way is to simply put the decimal version of that at the end. And even though I mentioned that we interpret these addresses in IPv6 in hexadecimal, this particular conversion doesn't actually convert this into hex. It simply puts it as the same numbers, even though it's really represented as hexadecimal here. But this makes it very easy to see. If you see that traffic going over the network and that IPv6 address has 192.168.1.7 associated with it, then you know it's associated also with the same device that has 192.168.1.7 as its IPv4 address. If you have a device that's not dual stacked, it may only support IPv4. When that traffic gets to an IPv6 network, we may convert it to a different address on IPv6, but what we'll do is put 4 Fs right in front of that IP address to specify on the other side when it gets there, we need to put it back into an IPv4 form. There's another type of technology that we use to transition some of these networks between IPv4 and IPv6, and this type of addressing is called 6-to-4 addressing. That's all one word, 6-to-4. I didn't make a mistake there and not put spaces in. That's the actual name of that addressing scheme. And what that allows us to do is take this IPv6 traffic and send it across an IPv4 network. The IPv4 switches and routers don't even have to know that within that packet is an IP version 6 communication. The conversion process is one where we take the IP address 192.168.1.7, we put a 2002 in front of it, and then we convert the IP address to hexadecimal and add it to this as well. That's one of the ways that you're able to tell with that 2002 there that that is a 6-to-4 address. For this to work properly, it has to use relay routers that communicate out over these IPv4 networks. And there are a number of relay routers that you can see out there in the world. Another thing about this is that it uses IP protocol 41. This is not the same protocol that IP version 4 will normally use to send TCP traffic or UDP traffic. It's a very specific kind of IP protocol, and in many cases you'll find a firewall may prevent that traffic from communicating. So it's not a perfect addressing scheme, and it really is designed to allow us to transition between our IPv4 networks and into IPv6. A very common way of sending IPv6 traffic between two endpoints is to simply tunnel the IPv6 traffic inside of IPv4 packets. This tunneling process can be done a number of different ways. A very common way is one called ISATAP. This stands for Intrasite Automatic Tunnel Addressing Protocol. And it allows two IPv6 devices to communicate to each other directly, and they simply build a tunnel that they then send all of that traffic through. It's not really designed for site-to-site communication across the internet. It's really designed for intrasite. You're really communicating within a single location. You can easily identify ISATAP traffic because inside of the address that's used is 5EFE and then the IP address, the IPv4 address of the workstation that's sending this traffic. One type of tunneling protocol that is also popular is one that comes in Windows called Teredo. Teredo allows you to tunnel IPv6 also within IPv4, but it also allows you to NAT this traffic. So you can do communication with Teredo over the internet from one site to another. It can be NATed on one side and NATed on the other side, and yet this tunnel continues to function. So very, very flexible, and it's something you could even use in your Windows 7 machine right now, right out of the box, and be able to communicate via IPv6 to other devices on the internet. You don't need a special router. You don't need special switches. You're able to do this today. You'll notice that the Teredo traffic is going to have addresses that start with 2001. And if we look at the configuration of our computer, and we're going to do this in the IPv6 video, you'll just see just how easy it is to bring up your addressing, have a look at what your Teredo settings are, and without any other configuration, simply communicate to another IPv6 device over the internet. That's a lot of technology to prepare you for the IPv4 and the IPv6 videos, but I think that once you get to those videos, you'll start to appreciate some of the things that we covered here. Let's see what we've learned from this video. Our first question is, what IPv4 protocol is used to automatically assign IP addresses? And if you recall, there was a dynamic protocol that allowed that, called Dynamic Host Configuration Protocol, or DHCP. The second question is, 10.16.44.70 a public address or a private address in the IPv4 addressing scheme? Well, if we remember those internal and external, those private and those non-private or public addresses, we know that if it started with a 10 dot, that it was definitely a private address that we would use inside of our network, and that 10 dot address is not one that can be routed across the internet. And the last question, which IPv6 tunneling protocol is integrated into Windows 7 and can support network address translation? In fact, this particular tunneling protocol can support multiple network address translations end to end whenever you're tunneling that communication, and that is the Teredo tunneling method, to be able to send IPv6 traffic between two devices, even if you're going through a couple of NATs. That covers the information we needed to know about IPv4 and IPv6. We've covered the addressing, the protocols, and the technologies for those. And now that you have a basic overview of those technologies, we'll now be able to go to our next videos where we start configuring our Windows 7 to use IPv4 and IPv6. Thanks for joining us on this video. We've got a lot more absolutely free Microsoft videos. You can communicate on our message boards or send me a message. Visit our website at professormesser.com.